Hi everyone, in this lecture 7 we will discuss about the physical models for the semiconductor device simulation. This course is not for the device physics, therefore I will just briefly mention each model and show you how to use it. If you are interested, check our textbook on the semiconductor device physics. In the previous lecture, we got the IV curve. However, it did not consider any physical model. Now, important models are introduced. We are now using the G device. In the G device, a physical model can be specified by using the property statement. The property statement has only a spec, although you may write a body, but it is not recognized. When you write the property statement, in addition to the thing object name, model, and arguments should be provided. In the case of a model, currently we have only 6 options. For each property statement, specify only one model. Depending on the model, available argument options are different. I will explain it in next slides. Before discussing the implemented features, I would like to talk about statistics. Currently, the G device supports only the Boltzmann statistics. Following the Boltzmann statistics, the electron and hole densities are exponentially dependent on electrostatic potential and the quasi-Fermi potentials. However, for modern devices, it is desirable to adopt the Fermi statistics. Unfortunately, the G device does not support the Fermi statistics. We have to understand this situation. So, right now, on the statistics, we have nothing to do. The first effect to be considered is the bandgap narrowing. The bandgap is a function of the doping concentration. When we have a lot of impurities, those impurities contribute an impurity band and it effectively reduces the bandgap. There are several models on this effect, but in the G device, only the slot mom model is implemented. This model calculates the amount of bandgap narrowing using this formula. When the doping density is high, the bandgap narrowing is proportional to the log of doping density. In order to specify the bandgap narrowing model, your model name should be effective intrinsic density, all small letters and no space. Available arguments are old slopum, and no bandgap narrowing. Now, the mobility is considered. 3 effects should be considered in the mobility modeling. The first one is the doping dependence. Even for the pure intrinsic silicon, the carrier mobility is not infinite. It is because of phonon scattering. Therefore, the mobility is written as a function of temperature. It is related with the intrinsic material. However, when the doping density is high, the impurity scattering plays an important role. Again, there are several models for this effect. In this slide, as an example, the Massetti model is shown. The second effect is vertical field dependence. It is very important for MOSFETs. Also shown in these graphs, the inversion layer mobility has well-known universality. Although the substrate doping density is different, all structures follow the universal mobility curve. This curve is generated from the surface roughness scattering here and the phonon scattering. Only the Coulomb scattering term shows different values for different substrate doping density. Therefore, when you simulate the MOSFET, inclusion of the vertical field dependence is mandatory. Of course, for PN junction, you don't have to specify it. The last effect in the mobility modeling is its lateral field dependence. Here, lateral field means the driving force aligned with the current density vector. We have a mobility. It means that the electron velocity increases with the driving force. However, does it mean that the electron velocity becomes infinite when we have a very large driving force? Certainly not. Eventually, the velocity is saturated at a strong driving force. The mobility model must consider this effect. For example, the Canali model calculates the mobility under a driving force F using this formula. Up to now, we have discussed about three effects in the mobility modeling. Then, in the G-device, how can you specify a certain mobility model? In this case, the model name is mobility. Then we have three slots. One for doping, another one for vertical field, and the last one for the lateral field. For each item, you have available options, and it is noted that you may leave it empty. Without specifying a certain model, that effect will not be considered in your calculation. For example, this statement takes into account the doping and lateral field dependence. However, the vertical field dependence is neglected. Finally, we have recombination mechanisms. Previously, we have studied the continuity equations. However, they did not consider the recombination mechanism. When an electron in the conduction band moves to the valence band, we have a decrease of electron and hole numbers simultaneously. It is called as the recombination. Following the SRH, Shockley, Reed, Hall recombination center model, the recombination rate R is given as this formula. Here, taus are lifetimes, and we have NP minus Ni squared. It means that the recombination rate is 0 at equilibrium. Following a similar way, we can activate the SRH model. Of course, we have other recombination models. However, many of them are related with the breakdown mechanisms and not considered in this course. That's it for this lecture 7. You can now specify physical models inside the semiconductor device. Now you can perform the drift diffusion simulation with the physical models. Also, you can draw some graphs using the output files. So I feel that it is now time to start simulating the MOSFET. In the next lecture, we will simulate the MOS capacitor. Thank you and see you later.